Okay, our introduction is we have chosen scenario for our problem-based learning. Our scenario is about predicting mobile app RAM usage from number of active features and investigating whether increasing the number of active features in mobile app causes RAM usage to rise. This is the filler table for our problem-based learning, which is facts, ideas, learning issue, and action.
The problem focuses on determining whether an increase in the number of active features in a mobile app causes RAM usage to increase. The number of active app features is treated as the independent variable, which is X, and the RAM usage in megabytes is treated as the dependent variable, which is Y. So our hypothesis for this project is a change in the value of X must affect the value of Y variable.
This is the table of initial data set of number of active app features. For our case study, a total of 40 observations were collected. Multiple RAM usage readings were recorded for each number of active features to improve reliability and reduce errors.
Now we are going to have a look at our calculations. First of all, to determine the strength and direction of correlation between number of active app features, which is X, and RAM usage, which is Y, we need to compute the coefficient of determination, R squared, and correlation of coefficient, R. As we can see, the formula to determine the value of correlation of coefficient is given. All we have to do is replace the numbers that we get previously into the formulas. So after completing all the three formulas, we already get our value of R equals to 0.9835. Then we have to square the answer that we get. So upon squaring the R, we get 0.9673. Now we already have the value of R, which is 0.9835. Based on the table on the top, since the value of R is in between 0.7 and 1.0, we can conclude that the RAM usage Y has a strong positive linear relationship with the number of active features X. After that, simple linear regression was used to model the relationship between the number of active app features and RAM usage. The simple linear regression model is expressed by Y equals to beta null plus beta 1 X plus error. Now we have to obtain the best fitting line for this set of data. For this, we are using the least square method to estimate the unknown parameters beta null and beta 1 in the linear regression model. This least square method is a minimalization procedure for estimating the parameters. As you can see, this is the formula of the least square method. To obtain the value of beta 1, the formula is Sxy over Sxx. We already got these values previously in the correlation of coefficient method. So, we just replaced the values of Sxy, which is 5232.5, and the value of Sxx, which is 330, into the formula. Next, to obtain the value of beta null, we subtracted the value of beta 1 multiplied with the average of X from the value of the average of Y. So now, we already get the value for beta null and beta 1. Since we have the values of beta null, and beta 1, we can simply replace them into the linear regression model. The value of beta null was 107.47 and the value of beta 1 was 15.856. So, our linear regression model will become as y equals to 107.47 plus 15.856x. Finally, to obtain the best fitting line, we just need to find the values of 2 points. One is the value of y when the value of x is 0, which is the y-intercept. Then the values of x when the y value is 0. This is the new table for the values of x and y after finding the linear regression model. So in this table, we can see the best fitted values of y when we increase the number of x one by one as 1, 2, 3 and so on. Finally, this is the best fitted line of the scatter diagram for this linear regression model. As we know, we also used Microsoft Excel to get the linear regression model for this dataset. And as we expected, the linear regression model, correlation of coefficient R and coefficient of the determination R squared that we got from manual calculations and from Microsoft Excel are the same. In this problem study, the correlation of coefficient R value between the number of active app features and RAM usage is 0.9835. This value sits in between 0.7 and 1.0, indicating a strong relationship and a positive direction. So, we can decide that the number of active app features and RAM usage has a very strong positive linear relationship. This means that as the number of active features increases, the RAM usage of the mobile application also increases significantly. After that, the slope, beta 1 value of 15.856 indicates that for every increase of one active app feature, the RAM usage increases by approximately 15.86 MB. For example, activating additional app features such as background services, notifications, GPS, or animations requires more memory to store, process, and data. As a result of this study, we can estimate that each new feature contributes an additional memory load of approximately 15.86 MB on the mobile device. Then, the y-intercept beta null value of 107.47 MB represents that the estimated RAM usage when no active app features are enabled. Although a mobile app cannot realistically have 0 active features, this value serves as a baseline estimate for the model. The correlation of determination R squared value of 0.9673 shows that approximately 96.73% of the variation in RAM usage Y can be explained by the number of active app features X. This confirms that the number of active features is a very strong predictor of the RAM usage. Lastly, the linear regression model y equals to 107.47 plus 15.856x can be used for performance forecasting in the mobile app development, since the slope allows us to predict the RAM usage for different numbers of active features. For an example, if the number of active features increases by 15, the expected RAM usage can be calculated by y equals to 107.47 plus 15.856 multiplied with 15. As a result, for 15 units of active features, the RAM usage is expected to increase approximately to 342.31 MB.
Okay, let's see the comparison of software tool and manual calculation. Using statistical software such as Microsoft Excel significantly improves the efficiency and accuracy of regression analysis compared to manual calculations. These software tools automatically apply complex statistical formulas and can process large data sets within a short time. This reduces the time required for data analysis and minimize human error. As a result, our team could focus more on interpreting the result rather than spending excessive time on repetitive mathematical computation with the help of Excel. On the other hand, manual calculation of regression parameters such as the slope, intercept, and correlation coefficient involves multiple steps, including calculating summation and substituting values into lengthy formulas. These steps increase the risk of arithmetic mistakes, especially when dealing with many observations. In this study, the result obtained from statistical software exactly matched those derived from manual calculations, validating the accuracy of both methods. This demonstrates that while manual calculations are useful for understanding the underlying concepts. Statistical software is more practical and reliable for efficient and data analysis. Okay, in conclusion, this study shows that there is a strong positive relationship between the number of active features in a mobile application and its RAM usage. As more features are activated, the amount of RAM used by the application increases noticeably. The IR squared indicates that the number of active features is a strong and reliable factor in predicting RAM usage. Overall, the result suggests that mobile app developers should carefully manage and optimize app features to avoid excessive RAM consumption and maintain smooth app performance. Thank you.